Hello, and in this video we're going to be doing some linear models, and we're going to be fitting some data to a linear model and creating linear models from that data set. We're going to start off with doing this by hand. So we're going to be given a XY chart. First we would want to see what kind of form it has. By that I mean, is it linear to begin with? So what we want to do is graph these points and see what we have specifically for this data set. So we're going to put in two, going to label some numbers down here. Okay. And up here, similarly. So that we can plot some points here for X and Y. So this is X, and this is Y. Axis, so first number is 3, 0. Will be a dot right here, a point right there. 5, 2, 5, 2, 7, 3, 7, 3, 9, 6, 11, 9 is right here, and 13, 11 is right here. So this does look like it has a linear path to it. It means that there could be a line that fits this data. It's not going to fit exactly, but we can use it to predict some data points, either in the future or not. Okay, so what we would want to do is we would want to draw a line that we think fits the best in this data set. So let's say we think that the best fitting line may go through these values here. Okay, so we have that data set right there. So what we want to do now is create a model that follows this path. So we do have some points now. Maybe we should have it a little bit lower because there are a couple points that are below the line that are, so let's say we go with this line instead. So we have a couple points below and a couple points above, below and above. I'm going to take, for my ordered pairs, I'm going to use this ordered pair right here, which was 9, 6. I'm going to use this ordered pair because it goes through, my line goes through that ordered pair. And I'm going to use this one here, which is 5, 2. I'm going to use this one as an ordered pair. Now, if it didn't go through any of my ordered pairs that I had in the chart, what I would do is look to see if it crossed, like maybe it crosses here at 6, 4, or whatever it may cross at a grid coordinate, and then I would use that grid coordinate if it's not in the chart itself. That can help me find the equation. So we're going to take 9, 6, and we're going to use 5, 2 down here as my points. So first of all, to find this model, we would want to find the slope. So we would do that by subtracting the y's, 6 minus 2, over the x's, 9 minus 5. So we're going to get 4 over 4, which is the slope of 1. All right. All right, then what we want to do is to find the equation of a line. So we're going to use your point slope form. I'm sorry, your slope-intercept form. This is slope-intercept form. We're going to use slope-intercept form. We're going to know the slope, so we know y equals 1x plus b. We're going to take one of these points. We're just going to use 5, 2 here. We're going to plug it in to find out what b is. So y is 2, x is 5. So that means that's what we plug in. We would then solve that. We will get 2 equals 5 plus b. So b is going to be -3. So my equation for this line is y equals x, because we don't have to put the 1 minus 3. This is my model. Now it's pretty good fit, but it's not going to fit every data point, so that would just get us close to the data points that we have listed here. So that's using a hand method by hand. So you graph it by hand, you find some data points that fit on your hand graph, and you use your slope equation and your slope-intercept equation to find the equation of the line. Okay, so next on this would be to fit a linear model using Desmos. So we're going to do an example that was found in your worksheets that you can find in your document folder. So I'm going to be looking at this document here, this handout. It's found in your week 4 document folder. It's for section 2.4. So we're going to start here. It gives us some information about trends of carbon dioxide concentrations. It tells you what it has in 1960 and what it has in 2000. They're going to use 0 as 1960. So 0, this is going to be 1960. But they're going to put 0 there to make it easier, and this one is going to be 20 years past that, so it's 2000, but they actually use 40. Okay, so that just means that you're going to have to, whatever year you're going to put in there, you're going to have to subtract it from 1960 to put the answer in your equation. You're not going to be able to put the year in there. Okay, so we're going to go through the process that we just did with the previous problem. We're going to find the slope. All right, so that's going to be 369.4 minus 316.9 over 40 minus 0. Okay, now it says here we're going to want to write this in a decimal. Okay, so let's figure that out. So 369.4 minus 316.9, that's going to be 52.5. 52.5 over 40. So if we divide that by 40, we get 1.3125. So it says appropriate units here, so, and we're going to look at this in terms of, it's going to be parts per million. That's what the top numbers are, parts per million, and the bottom is years. So your units are going to be parts per million every year. So that's your growth. Basically, we're growing 1.31. So parts per million per year. Okay, so that's what that means. Growing 1.3125 parts per million every year. That's what we're growing. Okay, now it says find an equation. So we're only going one decimal place here, so we're going to round this slope to one decimal place. So we have our equation, y equals 1.3x plus b. Now what's nice about this one is they gave us the y-intercept right here because it gave us 0. So the b value is this, because if we put in 0 for x, it drops out, and y is 316, so that means my equation is, without doing any work, is 1.3x plus 316.9. So this is the initial value anyway, so we're starting there, the initial value. All right, now we're going to use Desmos to do this thing to see if we have a more precise equation that fits the data a little bit better. All right, so we're going to go to Desmos here, and we're going to plot the data. So first of all, we would need to have the data. All right, okay, so I'm going to move over here to this point. Here's my data, here's my Desmos. I would go to the plus item to put a table in instead of an expression. Okay, now I'm going to put in my x for my years, so it goes 0, 10, so 0, 10, 20, 30, 40, and 50. And this year for 50 is 389.8. 369.4. 30 is 354.2. 20 is 338.7. 10 is 327.7. and 316.9. So let's just double check, make sure we have all the right data points in there. It's bad if we don't have the same numbers, and it will give us the wrong information, and that would be bad. Okay, so we have the right information in there. We're going to go over to Desmos here and see if we need to plot it. So first of all, the chart's not going to see it here, so we need to reset the window so that we can see these data points. So my x-axis goes from 0 to 50, so I'm going to start at, so that I have a little bit of space here. Whoops. I need to go over here. I'm going to go here. So I'm going to start at like -10 for the x, and I'm going to go to like 60 here on the thing, because my numbers go 0 to 50 on the x's, 0 to 50, so I'm going to give me a little bit of space on the top and the bottom. The y-axis starts at 316, so we're going to go start at 300, and go to 389, so that's 400. We'll go to 400. Okay, so here's what I have. So looking at this, I have my data points. It looks like they are pretty linear. All right. So what we want to do now is to get Desmos to figure out the line. Well, and what we do is open another box here, and we just type in the equation of a line here. But instead of equals, we use approximately. So the little tilde symbol is going to be in there. So we're going to use these chart values though. So we have to use y1 and x1 because that's what is labeled up here. If you want to change these labels, you can use that different down here as well. But we're going to use this one. So we're going to start off with y1. Just type y, then 1. It puts a subscript automatically. And then we're going to say it's approximately what? So that's our approximate symbol here. We're not going to use equals because it's not going to be exactly the same. We want to use m times x1 and then plus b. So there's our equation. We're going to type in y equals mx plus b, except it's approximately. It looks like it does a nice job here. It goes through one of the points maybe. It gives you the statistics down here on the thing. It tells you what m is. that's the slope, and it tells you what b is. That's the y-intercept. And it's showing you right here where the y-intercept is. You can see that by hovering over it with your cursor, that is the b value that you found right here. Okay, so we're going to take that, we're going to write it into, we're going to do the sketch of this document from here. So this goes into here. We're just going to sketch it from this point. So we went up by 20s and we went up by 10s on that. Okay, so here's my sketch of this model. So here's my x, my y. Here's my x. I'm going to sketch it out here. 1, 2, 3, 4, 5. So we're going to give myself a little bit more room here for this, since I have a little bit more room. Okay, so we're going out 5 numbers. 1, 2, 3, 4, 5. We'll say this is 50. And this is 10. And then we're going to start out at 300 and go by 20s. So 320, 40, 60, 80, 400. Okay, so my data points are going to be 10 or 0, 316. So right about here. 10, 327, 327 right about here. So this is 340, 360, 380, 400. This is 10, 20, 30, 40, and 50. Okay, so 10 is about that. 20 is 338, so it's close to 340. 354, close to 360. 40 is 369, it's a little past that. And 389 right here. Okay, so we have this here. That's what we look like. Are the data points on the straight line? We would say no, they're not all on the straight line. Is the general somewhat linear? You'd say yes, we have a somewhat linear thing here. So now we have already done this part. It's given us the equation. We just need to write it down. So what we would do here is look at the equation here. So that's going to be we have right here. Okay, so let's put that there. It says to 2 decimal places. So it's 1.44. Y equals 1.44 x plus 313.37. 313.37 to 2 decimal places. Okay, it says graph your line of best fit. We did that. Add the line to my drawing here, so it looks like it goes through 313, so it's a little lower. It goes through here, and it goes up like that. Okay, what's the line of the y-intercept? So this is 313.37. Include the appropriate units to explain the practical meaning. This would be the initial value of the carbon dioxide concentration. This is the parts per million initial value of CO2 concentration for 1960. Okay, some scientists warn that if CO2 concentration reaches 450, it will lead to irreversible catastrophic global events. Use a calculator to generate a linear model to predict when that might happen. Okay. So 450, that we would say that that's going to equal this y value. So we would set that in there, 450 equals 1.44 x plus 313.37. We would want to find the year. That's the x value here, or the year after 1960 anyway. How many years after 1960? So to solve this, we subtract 313.37. We get 136.63 equals 1.44x. We divide by 1.44. We get 94.8, 94.9 rounded to one decimal place. So that would be 94 years after 1960, which is 2054. So sometime during year 2054, we'll reach that model by using this model. All right, and that's the fitting linear models worksheet that's found in your packet. So that's how we use Desmos to do that. All right, let's go back to two other things that we need to do after fitting models to do this. We need to know the difference between interpolation and extrapolation. So in your model, so looking back at this model, if we are going to look for any year between 0 and 50, that would be interpolation, because that's inside the data set. Okay, so this is inside the data set. Inside data set. This is outside data set. It is very important to know that interpolation is usually a good way of estimating, but extrapolation may not be, because it may not continue to be linear. It may change from a linear graph to something else. So when we predict after 50 years here, we're using extrapolation. If we're predicting between 0 and 60, like maybe we want to know 1965 or 1975 or 1978. So if we wanted to do those years, that would be interpolation. It's in between the values that's given. So we can do that a little bit easier. These are more, this is usually a better approximation, a good approximation. And this may not be a good approximation, depending on whether the thing keeps going straight. All right. The last thing here is, in this section, is correlation coefficient. Now, correlation coefficient is the fit, a value that tells about the fit of the line to the data. So it's a number value. It's between -1 and +1. Now if we go back to this example that we had here, we actually, if we went back to the Desmos itself, which is right here, we have this value right here, this R value. It's called R value. That is the correlation coefficient. So in the problems, the R value is that number, and this number is 0.9929 in this example. So R equals 0.9929 is a very close to linear. Exact line. So 1 is an exact line with slope positive, exact fit. And this is a negative slope, exact fit. So as your data spreads out, you get closer and closer to the middle number, which is 0 here in this case. So close to 0, not a good fit. We can't make many predictions if we're close to 0. So if we had points going up like this, that's going to be close to positive 1, close to 1. If we had ones going down like this is going to be close to negative 1. And this further and further we spread apart, the closer we get to 0. So if we have something just looks like it's a mess of points that we can't really predict, this is going to be close to 0, because we really can't tell where the line's going here, because it's just dotted all around in kind of a circular fashion. So we couldn't really decide which way to go, so we're close to 0 here. All right, and that's a correlation coefficient. That's a R value that's given in the Desmos when you do the fit. And if you do any other thing, it will also give you an R value, which is that number.